Good afternoon, everybody, and welcome to today's webinar, Developers Introduction to GPU Computing. This is Kevin Askew. I'm Director of Sales here at TechXtend, and I want to once again welcome everybody. Today's agenda will include a brief introduction on TechXtend, followed by today's webinar hosted by Duncan Poole from NVidia, followed by a question and answers period and the summary. TechXtend is a value-added reseller of developer and infrastructure tools. It can be found on the web at www.techextend.com. Under our ALM worldview system sits NVIDIA's technology. Within that ALM worldview, we provide industry-leading tools for your end-to-end development needs, including defining, designing, developing, testing, deploying, and managing. So without any further ado, I will now pass things over to Duncan for today's webinar. Duncan?
High-performance computing organization of NVIDIA, and I'm here to brief you a little bit about GPU computing and also to introduce this a series of webinars that we are planning with TechXtend to allow some of the partners that are building cool developer tools for GPUs. We're all lining up together to try and give you guys a chance to understand the developer ecosystem that's sitting around GPUs and how you can use them. So without further ado, let me go into the presentation. So first we'll talk a little bit about NVIDIA itself, and then introduce you sort of basics on the GPU technology. Then describe some of the tools that are available from us as well as from third parties for programming GPUs, and then we can talk a little bit about what's coming next. So NVIDIA as a company makes graphic processing units, or GPUs, and we basically have three product lines that use this technology. High-performance professional designers or mechanical CAD engineers use our Quadro line, which is our professional graphics line. The people that want to do computing, number crunching with GPUs, image recognition, a variety of compute-intensive operations would use the Tesla product line. And people that are working on a desktop research scientist, say, or someone that's maybe a gaming enthusiast, those people use our GeForce product line. Also new coming to NVIDIA, or from NVIDIA, is our Tegra product line, which is built for tablets and emerging low power processors, and they have GPUs and CPUs in them. So NVIDIA's got quite a diverse portfolio of products for customers to use. With respect to higher performance computing, it's very interesting that the actual start for this was not really driven by NVIDIA. It was driven by research scientists that noticed that the same kind of math that you might do for, say, shading in games, you imagine playing a high-end video game and smoke and so on, all those same mathematical operations for imaging are actually used a great deal in science. And so beginning in 2004, people started to use some of the traditional programming tools, at the time the language was called OpenGL, to actually do math. Since that time, we developed a language that's built on top of C, the C programming language, called CUDA, and we're now shipping, we're almost ready to ship version 4.1 of this development environment with a whole bunch of rather mature tools. The company itself is around 5,500 employees, and we're about $4 billion in revenue. So we're not going away. And for those of you that live in the high performance area, the big benefit here is that the commodity market for gaming PCs is actually able to drive down lower price points for doing number crunching on those same units, with, of course, some special features for the compute industry. We can talk about those briefly in a minute or two. do this right here. So in terms of GPU developers that are actually trying to use GPUs for computation, we've been tracking both the number of citations that have come in this area, as well as we have an extremely active research arm in NVidia that works with educational institutions to promote the use of GPUs for computation. I encourage those of you that are academics listening to this call to visit research.nvidia.com and see different ways that you can engage with us. But roughly 100,000 active GPU developers is measured by our downloads. 400 universities are teaching it in over 1,000 clusters worldwide. We also have CUDA centers, and this is something that happens out of the research organization, which are basically centers of excellence like Harvard and UIUC and Stanford and several places overseas like TITech that are making a serious effort to push the boundaries of research with the use of GPUs. So if you look at just last year, there's a list called the top 500. There's supposed to be the top 500 most powerful computers in the world. And you'll find that last year, in the 5 of the top 500, 3 of these giant systems are actually hybrid clusters, as we like to call them. They're clusters of CPU nodes with a GPU attached inside it, and the actual performance that they get is an aggregate of the performance that you get from a GPU and the performance that you get of a CPU. The benefit that this has is that the power requirement for computation has dropped dramatically. In fact, they often talk about how the cost of the system for supercomputing is now no longer the bigger issue, especially in Europe, where the power that you might use to run it is becoming a dominant factor. So good progress in the absolute high end of GPU usage. In terms of who are the developers and what industries do they work in and where are they trying to use GPUs, there's strong penetration into oil and gas and into academic use, as well as into government use, which you could probably have figured out from the prior slide. I'll talk a little bit about some of the work in life sciences where the computational problems that they face run so long that any kind of leg up on getting higher speeds and greater throughput is a real boon to that science. There's also some use in different kinds of specific simulations in finance that are attractive for use of GPUs, as well as you could imagine a connection between, say, some of the mechanical CAD needs and visualization needs are often coupled to some of the computational needs that they have as well in manufacturing. So the basics. So if you had to walk away with one message today, it would be NVIDIA is offering a broad enough product line now that it's possible to get started with CUDA, probably on your laptop if you have one that has an NVIDIA part with it. You can actually develop today using that hardware and write C programs or Fortran programs if you wish, or Python programs if you like, on your laptop that could execute on your laptop. So it's basically an environment for which an initial development could be done. You could then choose to go out and buy a gaming card or a higher-end Quadro or Tesla card and put it in your workstation and effectively have the power of a small supercomputer beside you to do additional development work. And then finally, obviously, in a clustered environment where clusters require hardware that's reliable, that isn't overclocked like a gaming card is, or that has features like error correction in all of its data pathways. That's where the special Tesla part in particular comes into play in clusters. So the message is, if you have a laptop, please start looking at trying this now. In terms of a developer ecosystem, I like to show this up front before diving into the minutiae about one particular facet or another of the GPU or of the tools that NVIDIA provides. And really to point out that there's an array of support organizations and support tools. There's consulting and training available from us for free and from other people. Some people are even willing to help you port your application to use a GPU for a fee, of course. MATLAB and Mathematica have implemented GPU components in their libraries, in their math libraries, to accelerate things like matrix multiplication and other aspects of linear algebra. There are debuggers and profilers that are shipped by us and shipped by third parties as commercial products that we can talk a bit about today. Similarly, we can talk about compilers and some of the newer parallelizing compilers that represent a really elegant solution for quickly developing code to run on the GPU. And then finally, there are all kinds of libraries, and potentially these are the simplest way of getting engaged by just using a library with your code to get some speed rather than having to develop the code yourself. And finally, virtually every OEM right now is shipping a product that has an NVIDIA part in it that's capable of doing computing. So please, please keep that in mind as well. So what does a modern GPU look like? Well, today, a modern GPU, this is a hard graphic to view, but each of those individual green boxes is a compute unit. It's able to do a floating point and an integer operation at the same time. It's clocked at 1.5 gigahertz. So if I compare that to a CPU, probably your modern CPU is running around 3 gigahertz, maybe a little more. And you might get maybe 6 of them, say, if it was a Westmere part, in a single chip. In a single GPU, which, by the way, is the largest semiconductor of its type that's built, it's much larger than a CPU, you can have 512 of these processing elements that are able to execute in parallel. So that difference of 512 versus 6 is one of the major ways that you get much more performance out of a GPU compared to a CPU. Another big benefit is that the GPU uses a higher class of memory, uses DDR5 memory, which is clocked at a much higher rate than typical CPU DDR3 memory is clocked at. So if you got a problem that you can, and to give you an additional feeling for it, there's on a high-end part, there's 6 gigabytes of DDR5 memory available. So you could imagine shifting an entire problem over to a GPU, having it live resident in GPU memory, and then having 512 processing elements all able to simultaneously execute against it to do some calculation. Another thing that it's a little bit beyond the basics, but they call these things streaming processors because in a perfect world, if you had a lot more data that you had to move back and forth, you can do computation and overlap at the same time that you're doing the computation. You do transfers of additional data. And then basically these 512 elements all execute in parallel instructions that run on the GPU. Okay, so I think that's reasonably clear. There's lots of characteristics about this from an architectural perspective, like the 512 units are actually organized into blocks of 32, and for the benefit of things like program synchronization, those 32 units are able to execute together in a way that's more optimal than, say, trying to synchronize across all 512 elements. So there's some fine print about the best way to do synchronization and shared memory access within the unit. But if you just keep in mind that those features are available, you'll actually find that it's a pretty approachable programming model. So today, a modern GPU, and I think I mostly covered most of this, the highest end part we ship is actually available in servers from IBM and Dell and HP and Cray. This is the M2090 part, and this part has the 512 cores that we referred to. The memory bandwidth that you get, the DDR5, is this 177.6 gigabytes a second. And then the processing units are actually able to execute single precision faster than double precision, but you can see that the number is, the teraflop number is actually very high for this part. There are other GeForce parts that are pretty much as fast as this. They don't always have the same double precision capability, but If you're working in a desk side situation and you're just wanting to explore this, you may get spectacular performance out of using your GeForce part for some of this work as well. So programming, what does it look like? So creating a C program, it looks like standard C that's passed into our compiler. The compiler framework is actually an open source framework, and it invokes a program called NVidia CC. This one splits out code that has special directives in it, where a separate compiler is used. This NVidia compiler is used to produce a binary that executes on the GPU. At the same time, the balance of the code is passed to your favorite C compiler, and it actually creates the executable that would run on the CPU. So you don't give up anything in terms of your standard programming tools for your CPU. You're really just trying to split out parts of that code, and you do that with some special hints that I'll talk about in a second. And that's what's passed on to the GPU, along with libraries that NVIDIA provides to accelerate things like math functions and so on, so that you can make calls to those directly. So the real trick is you annotate your code to make it parallel, and then you compile it. And once you've compiled it, when you run it, it automatically takes care of transferring the actual executable over to the GPU and then executing it and finally returning. So what does it look like? I don't have a pointer to do a good job of describing this, but you can see the portion of the standard code that would normally execute in serial fashion on the CPU, and then here is what that code looks like when you want to run it on a GPU. And basically it's forking off a block of threads and then running in parallel. That triple chevron was the annotation I'm describing to. That's where the magic happens. It says how many blocks and how many threads to launch, and then what the computation is that you're going to run. So you can see that it's fairly straightforward in this context. I think the important thing to note is that I'm not trying to send a message about you should move your whole program over to a GPU. The real truth is you should move the portion of the program that can benefit from running in parallel over to the GPU and run it there, and then look at that balance and benefit of running CPU and GPU together. So it's not one or the other. Ultimately, I think it's a both. So what are the steps? The normal steps that you have to think of from a developer's perspective is you have to profile your code. Not many developers do that, and identify where the real hot spots are. Consider using directives, this chevron syntax and so on, to describe how you're going to make your program more parallel. Measure the performance that you got, and then go back and fine-tune, if you like. It's an optimization cycle. So what does that mean? It means you need a compiler, you might need a debugger, you surely need a profiler, and then you may or may not need some way of describing or having a good view into the overall balance between CPU and GPU execution. If you think about what kinds of programs one should choose to move to a GPU, this graphic is attempting to describe something called Moore's Law, which probably many of you already have some knowledge of. But you can see in the top case that here I have a program that has a relatively flat profile. It may do a bunch of serial work. There's a portion that can be done in parallel and then a bunch more serial work. Now, if I spend a lot of time, or if I spend some time, I may be able to optimize that middle 1 hour in parallel and get maybe a 12x speed up by doing it. But the overall effect it has on the runtime of my program isn't that great, simply because the fraction of the code that I can parallelize is only small. So this is a case where you could either call it, it's a bad example of code to spend a lot of time on. Not such a bad example for things like directives, where with some of our partners, such as PGI, you can actually simply insert some lightweight directives and let the compiler try to speed it up for you. Now, on the other hand, the example below, where you have a program that spends 4 hours in execution that you can identify as this is something I can do in parallel. If I can reduce that down to 15 minutes, well, then that has a pretty good speed up, and it's a much more spectacular benefit. So, the programmer effectively has to make this trade-off and decide, is their program really suitable for parallelization across this many programming elements or processing elements? So how can we make this easier? So from the standpoint of working in the ecosystem of software partners, which is, I guess, where I come from, there are several organizations that are releasing libraries that provide GPU accelerated features. That is, you don't have to do anything except call the routine. That would be the minimum case. The next best case is you actually think a little bit about where you want your data to live. And the reason why this matters is because let's say you wanted to do a whole bunch of different operations on the GPU, different math operations one after the other. Well, you can call the routine and ask it to return the results always back to the CPU, or you can make a slightly different argument call or routine call and just have the results retained on the GPU and save yourself the time for memory transfer. So these library vendors supply routines that are designed to do this, either leave it on the GPU or not. Also, many of these vendors supply options for when to use a GPU and when not, and they hide the decision making for this. And the reason that this matters is sometimes, let's say you're doing a matrix multiply. If it's a small enough vector that you're multiplying, why would you go to the GPU? It might take you more time to launch it than it would if you ran it on the CPU. And this is especially true with some tuned packages from Intel, like the MKL library, are pretty good up to a certain matrix size. It doesn't make any sense to move it across. But companies like EM Photonics have released libraries where they know where the crossover point is, and that's actually what this top graph represents. So effectively, for small matrix size, you follow that light dotted line to get better performance on the CPU. But the moment the GPU actually performs faster, which happens once the matrices get big enough, at that point you should move the data across. So this is a case where with the help from some libraries, you don't have to think very hard about how to make use of a GPU in your program and get some really great performance. There are other organizations that release libraries, and they're listed on the left here. Magma is an open source project that Jack Dongara is spearheading, where he actually makes use of the CPU and the GPU at the same time for the math. So he takes a slightly different approach then. It's not one or the other, it's actually using both. And companies like RogueWave with their IMSL library, they can call the GPU and perform GPU functions, and then they also let you pick your favorite library that you want to use on the CPU side, just in case MKL isn't the one that you want to use. So past all this, we also have a variety of libraries that NVIDIA supplies. There's BLAS 1, 2, and 3 libraries, sparse matrix multiplication libraries, fast Fourier transforms, as well as some other performance primitives and random number generation for people that work in the, important in particular to people that are in the finance industry. So past libraries, the next most simplest approach would be to use directives. And for those of you that have been doing any amount of parallel programming in the past, an example of a directive environment would be OpenMP, where on a single processor, they might have written a program that expresses parallelism. It uses these lightweight directives, and then in the current days, without GPUs, it would attempt to run that program on all the cores that sit inside your desktop processor, say. So there are similar directives, and they look like the Pragma ACC region that you can, I hope, read better on the screen than I can see. With this single Pragma, that says, look at the loop below, figure out how to allocate memory on the GPU, how to pass over the variables in question that I want to perform an operation on, perform the operation on the GPU, and then return it. So this is what a directive does for you, is it takes care of all the housekeeping, if you like, and then obviously there's a good compiler sitting behind it to issue the optimal instructions that would then run on the GPU. So accelerators are a great way to get some performance out of running on a GPU without necessarily having to learn memory management or synchronization. So it's great for lightweight exercises like that poor code profile example that I showed you. There are companies like Cray who believe that directives are the way to go, and that and that you can get almost all the performance you might want without having to be a coding ninja. Of course, NVIDIA's standpoint is we like the ninjas, right? They play games, and besides that, if you really want to get that last erg of performance out of the GPU, we have to expose tools to let you do that. So that's why it's important that we have this range of options for you that run all the way from a high-end compiler like CUDA through to simpler methods like libraries for getting some performance out of your GPU. So having maybe picked your compiler, if you're going to use one at all, NVIDIA offers many other debugging tools. So free with the downloadable SDK from NVIDIA, you get cuda-gdb, so standard command line GDB, where you can set breakpoints on the GPU and actually debug the code and look at register values and so on. It's shown in a visual representation here because people that use GDB a lot sometimes put it inside of a favorite editor like Emacs, and they're actually able to have a nice, efficient compilation cycle. So that's for Linux only. We also ship, for Windows developers, the CUDA Visual Profiler. Excuse me, this one is also available for Linux as well. A profiling tool to help you identify bottlenecks in your code and also look at the resultant profile of the code on the GPU. Excuse me. So these last two are Linux tools free from us. We also have free a parallel debugging tool called Nsight. This is a plugin into Visual Studio that can be used to program GPUs and inside of Visual Studio. It's also used for profiling those tools, so not just debugging, but profiling as well. And can handle CUDA, which is the programming language that we highlight for compute purposes, but there are other ones. It also handles OpenCL, which is a common open standard that some people are interested in using, especially if they want to have their code execute this way and run on CPUs alone. There's also Direct Compute, which is a Microsoft standard for computation, shortly to be replaced by other standards from Microsoft in the same area. Direct 3G and OpenGL. So these are graphics standards as well, and this tool can support people that want to program to any of those programming models. So this is the example of the same profiling, the same tool being used for profiling, and you see code execution on the various blocks here inside the GPU itself. It's a fascinating tool. So some success examples. I'll talk briefly about this life science example I said I was going to in the beginning. The way to think about how life scientists use GPUs is, if they could, they would try to accurately simulate, say, a drug interaction inside your body. And if you think about what that means, well, your body's mostly water, and pretty much all of those reactions, if you want to talk about them at the atomic level, have to operate at the rate at which chemicals like water will react. So it turns out that that's actually measured in femtoseconds, which is 10 to the minus 15th second. And light moves about 0.6 millimeters in that period of time. And that's if you wanted to model it accurately, you would have to be measuring in femtosecond steps and actually look at how a chemical might combine in water with another chemical to estimate a drug reaction. Well, AMBER is a very popular package that's used in molecular dynamics, and they literally have to run these kinds of calculations for days to weeks, especially if you want to simulate, say, several thousand atoms. And so because of this voracious need for compute cycles, they chose to port to the GPU. There's papers out on this if there's anyone on this phone that happens to be in this life science area. So here we have a case where the bars, the higher bar, the better the performance. That's the amount of drug reaction time you could actually measure in a single, or simulate in a single day. And you can see that with the highest end CPU at the time that this study was done, it would run about 14 nanoseconds a day, and on a GPU you get about 58 nanoseconds a day. And the larger the molecule, the greater this performance delta actually gets, because effectively you get a greater degree of parallelism that takes place because there are more atoms you can operate on. So there's a slightly bigger benefit here because of that. Another one that's also in the life science area, here we have an example of a code running on a cluster. We haven't talked too much about the high-performance computing aspect of this, but as I said in the beginning, one of the places where GPUs are being adopted is in clustered supercomputing. So this means you have to run a problem that's so big or so long that you need to run it on a whole bunch of processors at the same time, and even a single GPU would not be enough. You need thousands of them. So here we have a case where the people at the University of Illinois, UIUC, actually who program and develop NAMD with their collaborators, that they created a version of NAMD that runs on a GPU and a CPU. It's free for download. You can go to the website and pick it up. And that additive benefit of adding a GPU to the CPU gave you this curve so that, basically at any point in time, you gain performance by having a GPU on the node. And this performance improves even as you go out to 16 nodes. There's a huge gain to be made. You basically, effectively, you double your performance by having GPUs inside the node as well, compared to CPUs. So, what's coming next from us and in this series? Whoops, clicked too far. So, the next one is a discussion really about these accelerator compilers from PGI, as well as they are our collaborating partner for developing CUDA Fortran. So this is for those of you that want to program in Fortran on a GPU. It's quite available. We also have partners that are going to speak to the commercial debugging solutions that come from companies like Alinea, where you want to debug an application that is hundreds or thousands of GPUs and CPUs all cooperating to solve a problem. Well, how do you debug that class of problem? So Alinea vends a product that runs on a single GPU on a single node, but scales all the way up to this kind of cluster debugging aspect. For more information about this, you can go to developer.nvidia.com, where you can download the NVIDIA SDK. There's also forums at the same location. So we have everything from videos for getting started with CUDA to books that you can buy that have been co-authored, or you can download the chapters directly from the website, as well as all of our principal debugging tools are available on this front. We also have a developer conference that's happening in March. It's in Santa Clara, California, and there's probably about 3,000 developers from around the world, and obviously tools providers and others get together to talk about how to program GPUs best and what to do with them next that's best. So I'm going to stop here for a second and then see if there are any questions that have come through in Q&A that anyone might want to ask at this point.
Duncan, I do have one question from somebody, and was a GPU originally a graphical processing unit, but is now dedicated to high-speed computing and not for graphics at all?
Well, it's interesting. So the term GPU was coined as a graphics processing unit, and there have been people that have been playing with that term. They sometimes call them GPGPUs, or general purpose graphic processing unit, and that's to try and explain that it has more functions than just to, say, do shading for video games, that you can actually do math, like we've been talking about throughout this presentation. So NVIDIA for a while built cards that didn't even have a graphics output on it. It was just, obviously we have graphics cards, but we have these cards with no graphic output, and they're basically a block that sits inside your computer or on a node. So it went that way for a while, but we discovered that people really wanted to compute and to do graphics. So now even our higher-end compute-dedicated cards have graphics on them, so you can do graphics and compute at the same time. And I do want to continue to point out that for this audience, especially that are C programmers just getting started, you should start with your laptop or with your favorite gaming card from NVIDIA, and I think you'll find you can make great strides in understanding how to do this and taking advantage of what you can do here, either on Windows or on Linux.
Okay. I'm an assembler language programmer. Can I do the equivalent on a GPU where I work at the register and memory transfer level?
The answer is yes, and if you're that kind of programmer, you probably understand the challenges that are in front of you. Think about 500 of these cooperating together and the synchronization issues. Bear in mind that every GPU has its own scheduler, and so imagine scheduling, say, 10,000 threads across 512 processors, and then drilling down to the assembler representation. But you can, and there's two levels to doing this. One is called PTX, and that is effectively the code that's emitted directly by the compiler for execution on any GPU. So this is to say any NVIDIA GPU, regardless of its amount of memory or number of processors. There is also a way to cause so PTX is probably where I would go first. There is also this thing called SAS, which is an even lower level machine representation that's directly targeted toward a specific GPU. And the way this one works is that the CUDA kernel that is compiled by NVCC is PTX, which is JITted on the fly, or just-in-time compiled on the fly, into something called SAS, and that's the final thing that's executed. So you could look at either. I suggest you start with PTX.
Okay. I write computational EM simulations, which involves the filling of large matrices through complicated numerical integration. Would the GPU mostly be useful for the linear algebra portion? I mean, the integration routines involve a lot of logic.
It's certainly definitely useful for the linear algebra part. I'm not sure of the science in your particular area, whether or not you want dense linear algebra or sparse. We have we have routines that are available on both sides. If you're a commercial entity, there's also partners that are very good in this particular area, this particular industry area, and you should contact me and I could link you up to some experts if you don't want to do all the lifting yourself. Outside of the pure math functionality, the trick will be to what degree can you stream this information to the GPU so that you can keep the computational units busy and fed while you basically compute and overlap compute with the data transfer. If this is achievable with the particular math functions you're trying to do or the particular algorithm you're trying to implement, then you can get really, really great performance. I'll also add there's an area called adaptive mesh refinement, and sometimes people tend to describe the algebra that they're best describing as one where there's successive refinement of certain areas of interest. Again, I'm not sure if the EMR field, the area that you're in, is in that area or not. But if they are, again, we could have a longer conversation.
Okay. Is the OpenMP-like derivatives compiler available for Visual Studio 2010?
So here's an interesting case. If you're a Windows developer, you have a bunch of choices. The one that's emerging from Microsoft is AMP, A-M-P, and I would encourage you to look at it as a potential programming target. You can, however, get, CUDA. Let me think about this. Yes, I think from our partners, like PGI in particular, you can get a version of the Directives compiler that will run on Windows, and then you could use that.
Okay. Are there any Macintosh tools available?
Yes, the PGI compiler also runs on the Mac. From NVidia, I believe the GDB version runs on the Mac. Pretty much everything runs on the Mac. There is some fine print about whether or not it runs on both 64 and 32-bit that escapes me at this time. But there really shouldn't be any problem with doing base level development. I know also that that Apple is strongly behind OpenCL. I think if I was doing pure compute, I might lean towards CUDA, but that's me and my biases on this subject, or toward directives.
Can CUDA C code be mixed with C++ programs?
So here the answer is sort of, and I'm going to give the honest answer. I think it's sort of yes and maybe. There are people that do write in C++, but they end up basically taking advantage of things like standard templates without using all the full-up features of C++. So it's sort of like C with templates, if you like. On this front, I suggest you look at Thrust, which is a library interface that's good on this for this. There's another one which isn't quite as popular, but some people like, called Boost. So I would start with Thrust, and then, if you must, go towards Boost, with the caveat that Boost tends to pull in, it's a fairly heavyweight package that may pull in more than you want from a standpoint of, if you're a minimalist like I am, you probably want to go with the smaller of the two packages. So I would suggest you look at Thrust.
Okay. The benchmark showed 2 to 4x improvement. I've seen other reports of 18x. What's realistic?
So it's sort of this getting started question with how much work you want to put into it, right? It's a cost. Your efforts are going to be tempered by the speed of light for the particular algorithm that you're using. I think it's very realistic to look at, say, 7 or 8x. With work. I have seen people get 50x with a few hours with directives, but boy, your program has to really suit that sweet spot to do that. So I think I'd be realistically hoping that you might get a benefit of say 2x in a period of 4 weeks, and that 4 weeks of thought, probably less, and especially using directives. And that if you want to put more effort in, 8x I think is quite achievable. And then, but again, it's all about your code and what your code does. So, so I don't know how to temper realism in this context, not knowing your code.
All right. Is it possible to make a DLL, I believe, or DII with CUDA-C that can be called from the .NET framework?
There is an effort called GPU.net. You can Google for it and find it. These are the guys that I think are most advanced at using .NET functionality. It's from a company called Tide Powered. It's very funny spelling, so there's no ED at the end. It's Tide Powered. So you might want to take a look at that. The DLL aspect is interesting because basically what you have to do is wrap up an entire kernel that's going to run on the GPU. They're not, the GPU components are sort of monolithic. Yes, you can put a DLL around it that would call a CUDA kernel that then would go run on the GPU. It's a hard question to answer properly. I hope you understand what I'm saying.
Okay, and the last question that I have right now is high-end HP Intel boxes are now 8 processors by 10 cores by 2 threads, 160 threads. How many GPUs could I practically get on these? Would it be worth it?
So you can put we didn't talk about this, but the programming model for GPUs includes something called unified virtual addressing, where all the GPUs within a single box live in the same common address space. And the NVIDIA compiler is actually smart enough to hide some of the transfer efforts when you need to move data from one GPU to another. Those high-end HP boxes at least have 8 slots that can take GPUs, and you can do, there are people that build programs that run in parallel on all 8 GPUs at the same time. So you can get pretty dense within a single node, and it's quite practical to do so. It depends on your problem and whether or not it partitions in a way that makes sense for that kind of capability. At that point, you're talking about 48 gigabytes of DDR5 RAM spread across, 8 computational elements. So it requires a bit of thought to do it properly. There is also a functionality called peer-to-peer, where depending upon this fine print here, so you'll have to take there is some fine print, but the behavior that you get is when you move data from one GPU to another, you don't always have to go through the CPU bus to do so, through the CPU to do so. It can be managed and directly transferred from one GPU to another within the node. So these are features that might help you in that context. I hope I've answered your question properly.
Okay, and we do have one more question that just snuck in. I do MPI programming. How does CUDA or GPGPU support MPI programs?
So let's see if what can I say without leaking? So we have, NVIDIA has worked with Mellanox and QLogic to create this thing called GPU Direct, which the vision of which is that you can actually transfer data from one GPU on one MPI node through an InfiniBand interface all the way out through the cluster back to another InfiniBand interface to another GPU. And our goal over this next while is to do all of that without any CPU intervention at all. Now, we're not there yet. But today, we do have these features like peer-to-peer copy and the ability to, and also in the driver, in the current Linux drivers, the way we pin our memory is such that there's only a single copy that takes place when we move data from an InfiniBand allocated component of memory and a GPU allocated. So we've actually done some work to eliminate byte copies where they aren't needed. So the stacks that are tuned for this right now, there's the OFED stack, which I guess is OpenMPI, and I think since version 1.5.2, that this GPU Direct feature has been available. There are other implementations. DK Panda will be speaking about it at this next supercomputing coming up, but basically MVAPITCH, it supports some of these basic things that we talked about, but they have been doing research on taking advantage of these features in other novel ways. And so MVAPITCH is on its own development cycle. I believe they will announce the availability of a new capability at SC in MVAPITCH that will be available for download in that time frame. And finally, I know that GPU Direct features from NVIDIA work with Platform MPI, which is popular in some commercial areas. Hope that helps.
Okay. Do we have time for one more question, Duncan?
Sure. Okay.
Is there good support for CUDA on a Windows-based development platform, specifically cfound.net in Visual Studio?
Well, I think it's pretty good. I have to admit I'm a Linux guy, but from a Windows perspective, the fact that we ship this plugin for debugging and profiling is very good. NVCC obviously runs in that environment. For full-up.NET development, specifically .NET, I sometimes think that we should look to either Microsoft and its own efforts with AMP, A-M-P, or I suggest you take a peek at this company, GPU.net, and tell me what you think. I really want to hear about it, actually. My email is dpool@nvidia.com, and I'd be interested in your insights. And then finally, from an accelerator perspective, companies like PGI and their lighter weight accelerators are a good thing to consider. I don't know that it wraps directly inside of Visual Studio. That's perhaps the subject of a talk that they would give.
Okay, thanks, Duncan. I'm not sure if you're completely done with your presentation. Just go ahead and let me know if we can wrap it up here today.
Yeah, I think so. I talked about the developer conference, which I believe was the last slide that I had. Yes, there's nothing more to add. But, and I appreciate everybody's attendance. I hope you found this interesting, and I look forward to any follow-ups and email that you might want to have with me.
Okay, thank you, Duncan. And if anybody does have any questions or questions that didn't get answered, please feel free to email salesassist@techextend.com. It should be up on your screen right now. All right.
All right, again, thank you everybody for attending, and thank you once again, Duncan, and everybody have a great afternoon. Thank you.